to be what you want me to be, to find I'm blind to me, to feel so hollow without you, to run my city till blue.
Okay, in this video, we're going to discuss the commonly employed applications of basic external ballistics to classic long-range shooting. We're going to kind of start by summarizing the primary physics of external ballistics first. We're going to have to explain just a real brief physics review, particularly Newton's first law of motion. That will be absolutely fundamental in understanding the story of a projectile in flight. Once we understand some of those basic physics, we're going to be able to comprehend the components of a parabolic trajectory curve and why it's shaped like that. We'll also be able to understand how gravity affects a projectile's trajectory and also how the different components of drag affect a projectile's trajectory. In this basic external ballistics, we're also going to briefly cover wind velocity and wind angles and how to correct for that. And we're basically going to focus on the commonly employed methods of weapon zeroing, how to set up ballistics tables, and conduct firing solutions. Like I said, this video is going to be just covering the commonly employed applications of basic external ballistics to classic long-range shooting. So that's important that you understand. This is not getting into advanced external ballistics yet. I first have to kind of introduce the topic and make sure that we're all on the same page. And for a lot of you who are just starting out on this ballistic stuff, this will be a real good introduction to it. So this is probably a review for a lot of you, but in order to compare and contrast how it's done classically and how we're going to do it, you do need to kind of know how it's been done classically. So even though we're going to be getting into a lot more detail, you're going to want to know what most people kind of do when they're long-range shooting. So that's what the point of this video is, just a real basic overview of normal long-range shooting techniques. So before we get too far, we're going to quickly review some basic physics and a little bit of terminology here. So the number one main thing you need to be aware of is Newton's first law of motion. I don't know if you remember this from way back in the day when you might have sat in a desk or something, but let's review that real quick. Basically, Newton said, every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So basically, if an object is just sitting still, it's not going to move until an outside force pushes on it, right? Or let's say we have an object that is set in motion. It's going to continue in that motion uniformly without changing speed or direction, and it's going to go in a perfectly straight line forever, or until it encounters an outside force like maybe friction or gravity or some kind of force that's going to change its speed or direction. And that's probably another thing you might want to be aware of when we're talking terminology. When we're talking velocity, the common definition of velocity that shooters use is basically the speed of a projectile expressed as a distance per unit time. So basically feet per second, that's how fast your bullet is going. The common definition of velocity is not really correct, though. In physics, velocity refers to both speed and direction in the motion of a moving object. So change in direction or a change in the speed are both changes in velocity. So if you have a car that's driving 70 miles an hour and you turn it, it's still going 70 miles an hour, but you're changing the direction, you're technically changing that car's velocity. Now that's called a lateral acceleration, or the velocity is changing, the direction is changing. So that's something you need to also be aware of when I mention velocity here. Although most of the time we'll be talking about it in its common definition, but you do need to be aware of that probably. So let's start off by looking at some basic diagrams here. Now, this might seem a little goofy at first, but it's kind of important, and we're building a foundation so that when we get into advanced ballistics, you ain't going to be left in the dust. So what we're going to do is a real quick, this isn't a real formal diagram or a free body diagram. It's kind of an informal free body diagram that I'm going to do. This is a bullet here, okay? And the first thing we're going to put on this diagram is it's going to be sent into horizontal motion. And that motion is going to be a forward velocity, right? It's going to be traveling forward. When you pull the triggers, controlled explosion is going to send that sucker into flight. Let's say 3,000 feet a second. So just as soon as that thing starts moving forward, it's going to begin to experience friction, okay? Now, there's going to be, a lot, when we're talking internal ballistics, there's going to be a huge amount of friction as it's going down the bore. But let's just talk just external ballistics here for now. Once it exits the muzzle, it's going to be going 3,000 feet per second through the air. And the air is going to have quite a lot of friction on there. It's going to be a frictional force kind of slowing it down, pushing against the front of that bullet. So that's going to be one force acting on it. Now, if it wasn't for the atmosphere, according to Newton's first law, the bullet would continue going straight forward in its horizontal portion of its velocity at 3,000 feet a second forever until something made it slow down, until an external force acted upon it. So Newton's first law says that this frictional force of the air rubbing on the bullet is going to immediately start to change its velocity, and in this case, the horizontal portion will be reduced. So it's going to slow down the horizontal portion of your velocity. It's not going to be going 3,000 feet per second after it experiences friction. It's going to constantly be slowing down. The second your bullet exits the muzzle, it's also going to be subjected to the force of gravity. And that's going to be a force pulling straight towards the center of the earth. And it's going to be a constant force. Now, out of all the different components to the trajectory, and when you're talking mathematically here, gravity is going to kind of be your only constant that you're really going to be able to keep. Friction is going to be completely different depending on your different environmental conditions. That's going to change with humidity, air density, barometric pressure, lots of different things. The forward velocity, how fast your bullet's going, the ballistic efficiency of your bullet, like the ballistic coefficient, we talked about that earlier. That's all going to have a huge effect on that friction. So the friction portion of force here, that's going to be changing all the time. That's going to be the hard part. The gravity part, that's going to be pulling straight down at 9.8 meters a second squared all the time. It's a constant. Gravity is a constant. So what's going to happen, the second your bullet leaves the muzzle and it's subjected to the force of gravity, its trajectory will be altered. So its velocity will be changed. And when I say changed, I mean it's going to be changing direction and speed. It's going to be changing speed because of the friction in the front. That's going to be slowing it down. That's one portion of the velocity. That's the horizontal portion of the velocity will be slowed down. The vertical portion of the velocity is going to be affected by gravity. That's going to pull it down. So it's not only going to be slowing down horizontally because of the friction, it's going to be changing direction, which is also a change in velocity going straight down. So it's going to begin falling. And the way gravity works is it accelerates towards the ground. You know, when you drop an object, let's say you hold up like a pen, and you're just holding it out at chest level and you let go, it's going to start off real slow at 0 miles per hour, and then it's going to accelerate on its way towards the floor, okay? So that's the meters per second squared part of the gravity equation. It's accelerating on its way towards the ground. So the longer it's dropping, the faster it will be dropping per second, okay? So that's going to have an effect on the shape of our trajectory as well. And let's continue. So your bullet exits the muzzle. It's immediately pulled on vertically by the force of gravity. And you'll notice here on this next diagram, you'll see how the horizontal motion is starting to slow down. The arrow got shorter. And your frictional force is also getting smaller because the bullet is changing its velocity. The amount of friction is going to be dependent on velocity as well. So the friction is going to be changing. You noticed your force of gravity has stayed exactly the same, okay? So as the bullet's slowing down in its horizontal portion, the force of gravity is still constant. However, it is still accelerating the bullet towards the ground in a vertical motion. And then, so that's kind of how that works. Let's look at this in a different diagram. Again, this may seem a little goofy, but we're just trying to illustrate the effects of gravity on projectiles. And the point of this diagram is to basically demonstrate how when you fire a bullet perfectly horizontally, if you're just going to perfectly shoot it horizontally, it's not tilted up at all, it's going to be dropping at the exact same rate that a bullet would be dropping if you just dropped it out of your fingers and dropped it straight to the ground. So a bullet that has a horizontal portion of the velocity going 3,000 feet per second laterally is going to be dropping due to gravity at exactly the same rate that any object would drop at if you just dropped it sitting still. What that kind of shows is that your horizontal portion of velocity, the lateral movement, the 3,000 feet per second going sideways, is different and not really connected to your gravitational portion, the vertical part, because the vertically it's just going to drop. Even though it's flying sideways at 3,000 feet a second, all things being equal, the vertical component of both projectiles, the one going 3,000 feet a second and the one going 0 feet per second horizontally, the vertical part is going to be exactly the same. They're both going to be accelerating towards the ground at 9.8 meters per second. That's just raw physics. Now, there's going to be some minor things that happen when you have a shock wave and a Coriolis effect when you're actually covering ground on a spinning sphere. Forgetting about all those things, the raw physics of it just says that both objects will drop at exactly the same rate. Now, what's interesting here, and we'll do this animation in a second, is that, like we said before, when your bullet exits the barrel, it's going to have a huge amount of horizontal velocity. It's going to be going 3,000 feet a second. So it's going to be covering a lot more ground, especially initially, horizontally, than it will when it just starts to begin to drop. Remember, if you're holding a pen out in front of you and release it, the second you release it, it's going basically 0. That's its downward velocity. It'll constantly accelerate. It'll get faster and faster and faster the more it drops. So because of that, that's why you have the parabolic shape to a trajectory curve. And if you look over here at the FFP part, let's take a look at the black line. That's the trajectory curve. And the second it exits the muzzle, it separates from the angle of departure. That's the axis of the bore. So it begins to fall. It begins to fall straight towards the earth. Now there's a horizontal portion pushing it also to the right. So 3,000 feet per second to the right, and of course this is not to scale, but it immediately starts to drop. And the further out you get to the right, the more it accelerates towards the ground, right? It's because that's the constant force of gravity constantly pulling. Newton's first law says that it has to, in order to change the velocity or accelerate the object in any direction, there has to be a constant force. Well, gravity's constant, so it's constantly pulling and pulling and pulling and pulling more and more and more, towards the ground. So that's why it begins to accelerate towards the ground, towards the far right half of the trajectory, okay? And also, another thing that really adds to the shape of the curve is the fact that when we're shooting on planet Earth, we have this thing called the atmosphere that produces a lot of drag on the bullet, and the drag also reduces the horizontal portion of the velocity. So that's reducing while your gravitational part of the velocity, the vertical part, is accelerating. So that's why when you look at a parabolic trajectory curve, the front part is usually a lot more flat than the last part, because the horizontal portion of the velocity is a lot faster initially. And as the bullet begins to slow down, not only is that happening, but your gravity is going faster as compared to your horizontal portion. So that's why you have the really steep downward angles at the end of the velocity curve towards the terminus, where it's about to hit the target. It's coming down real steep, but as it exits the muzzle, it's a real flat part. It's because you have two different things going on there. Your gravity is accelerating downwards, and your horizontal velocity is decaying. So let's go ahead and play this animation now. And if you look, the first target with the green line, that's just the line of sight. That's not even, when I say line of sight, that's not where your scope would be pointed. The rifle is pointed horizontally here. But the target on the left is the one that's being shot at by the rifle. And the axis of the bore in this case, as we repeated a lot of times, is perfectly horizontal, okay? Now the second target on the far right there, we're just going to hold a bullet with no horizontal portion of velocity. It's not being fired out of a rifle. We're just going to grab the projectile and pinch it and then drop it. At the exact same time we fire the rifle from the FFP, we're going to be at the exact same level and height. We're going to drop a bullet right next to it. And this will kind of illustrate how both projectiles will drop at exactly the same rate. So let's begin our animation here. Okay, so we have the bullet. There's the bullet in the rifle, and there's the bullet just being held. It's not going to be shot. Okay, we fire the bullet. First step here we see is the one fired from the rifle is moved significantly in the horizontal plane and a little bit in the vertical plane. If you pay attention to the one on the right, which has just been dropped, it hasn't moved horizontally, but it's dropped vertically. Exactly the same distance vertically, mind you, as the one fired from the rifle. Now let's go to the next part of the motion here. Okay, the bullet has again moved forward in its horizontal portion. It's beginning to slow down a little bit now in its horizontal portion because of air resistance, but it is still accelerating towards the ground at exactly the same rate as the other one. See how it's at the same level? Okay, now it's going to move forward more, and again, it's moving forward horizontally, although it is still slowing down horizontally, and exactly the same acceleration towards the ground. And you can follow it all the way through. You see, as you get towards the end of the trajectory, now there's the full acceleration of gravity towards the ground, so that's why your curve is more pointed downwards, okay? And the horizontal portion of the velocity is much less than it was initially. So now the bullet's coming at a downward angle at your target, and again, it's at exactly the same height as the one that was just dropped. And then it will continue that way, and they'll both hit the target at exactly the same time. And just to illustrate the shape of this trajectory curve, if you can't really see it very well and you're not knowing what I'm talking about, let's compare it to, this is what a curve would look like if there was absolutely no air resistance and only the effects of gravity. It wouldn't be a parabolically skewed curve. It would just be even on both sides. So the peak of the curve is going to be right in the center here. This is if there was no air resistance. What's going to happen is that your bullet is just going to be traveling horizontally at 3,000 feet per second the entire time, all the way to the end. And the only reason that there's still a curve there is because your gravity is still accelerating the bullet towards the ground. So there's still a curve, but it doesn't have that skewed parabolic shape to it. And let's look at this other illustration here where we have the trajectory curve that is in the normal atmosphere, and you can see how it is more skewed. And highlight the area under the curve there to kind of get the idea. That's the parabolic shape we're referring to, and that's due to the decay of horizontal velocity due to air friction in conjunction with the acceleration due to gravity. So that's why you have that shape and not just a perfect, nice, even curve. So that was a little bit goofy of a illustration. Now let's show you more of a real one, okay? Let's just go on basically a flat landscape. And over on the left, the blue represents the shooter, the final firing position where you're going to be laying out with your rifle. And the T, that's your target, okay? This first line, this blue line here, highlight that a little bit, that represents the line of sight, okay? That is the line that your scope is going to be pointed. So your scope, your line of sight, you're looking straight at the target through the scope. So your crosshairs are going to be right on the target. So that's just going to be perfectly horizontal in this case, okay? Now, when you're trying to hit the target at long range, as we just showed before, if your axis of your bore is perfectly horizontal, if this is at any significant range, your acceleration due to gravity is going to pull your bullet straight into the earth way too early, right? So what we have to do to get around that is the line of departure, represented by this red line here, or our bore line. This is the axis of the actual barrel, okay, the bore. We're going to have to elevate that, just like an artillery piece, right? You're going to have to elevate that bore line. And we'll point out some interesting things here. And what you're going to have is the same pattern trajectory curve that we showed earlier, okay? If you look in, if you remember before, the bore line was perfectly horizontal, but you still have the same shape, it's just tilted up now. You'll notice that the black line, the trajectory curve, immediately after exiting the muzzle begins to separate from the line of departure, the bore line. So in respect to the line of departure, the projectile begins dropping immediately. Now, it's not dropping in respect to what's truly horizontal, but in respect to the departure of the bore, it is dropping. So when you hear the phrase or the term bullet drop, that's what that's referring to, drop in relation to the line of departure, okay? So if you take a look at the middle of the diagram here in the pink letters, you got the elevation angle represented in minutes of angle or milliradians. And we talked about different systems of angular measurement before. Basically, they're either based on degrees, that's the minutes of angle, or they're based on radius. And you can go back and watch the video on that if you missed that part. But basically, what that's talking to is the elevation of the bore above the line of sight. So when you're cranking on the scope, let's say you crank up your elevation to 30 minutes of angle. That's half of a degree, okay? So these are not really to scale. These illustrations are exaggerated to kind of show you what's going on. They're not going to be this obvious of a curve. It's going to be a lot more flat than this. But basically, your elevation angle, you crank your scope, let's say 30 minutes of angle. Like I said before, that is about a half a degree of elevation. What you're adjusting is the scope turrets. When you crank them, they're pressing on the erector assembly, and they're actually pressing down on the erector assembly. So as you're actually cranking physically, your scope is cranking down even though you're turning up the elevation. And what happens is that in order to still see the target in the center of your crosshairs, you're now holding your rifle at an elevated position. So the bore is actually pointed up as you crank your scope down. Although when you are cranking on your elevation, we will refer to that as up. But it's really the bore that's going up. So when you dial in your firing solution, what you're looking at is that line of departure. That's really the elevation setting you're talking about. So if you adjust your optic for 27 minutes of angle, that's talking about your bore, your line of departure will be elevated 27 minutes of angle, or almost half a degree. Or if it's 10 mils or whatever that you're going to be adjusting, that's talking about that elevation angle. It's a system of angular measurement. So that's how it's like an artillery piece. How much elevation, how much of an upward angle are you adjusting? And that's basically all your scope is doing. It's just changing your line of sight so that you have to change your bore axis. And obviously the way it works is if you have a more distant target, you're going to have to increase your angle of departure, your elevation. That's going to have to be higher in order to reach farther. If your target's closer, obviously you're going to have to bring down your angle because assuming you got the same exact loads that you're shooting, okay? Another thing I should point out here before we get too far is that the trajectory or the bullet path is not only affected by gravity, which we said was a constant. Gravity is the constant, but it's also affected by drag and by muzzle velocity, your initial horizontal velocity. So that's your initial horizontal velocity is going to be determined by your internal ballistics. And we're going to talk about that in great detail when we get into our advanced internal ballistics video. There's going to be a number of factors that change your initial velocity coming out of the bore, and that will totally affect the trajectory of your bullet path. If you have a lower muzzle velocity, obviously your trajectory is going to be short. Even if you have the same line of departure, you still have the scope adjusted at the same exact place. So your elevation on your rifle is actually the same, but your trajectory is going to fall short because of a lower initial muzzle velocity. If you have too high of a muzzle velocity due to weird changes with your ammunition or friction dynamics inside your bore that we're going to cover later, that will cause you to hit way high. And so that's a whole nightmare we're going to have to address there when we get into internal ballistics. So that's one major thing that can cause huge dispersion of rounds, is because of your horizontal velocity being different. Okay, and that can change from day to day too, with different factors. Another thing, obviously, is that will change your horizontal portion of your velocity. Like we said, gravity is a constant. I'm going to repeat that a lot of times. Okay, what's changing is your horizontal components, and the other thing that's going to change is your drag, and that will change with atmospheric density primarily. And there's a lot of ways to figure that out. Humidity affects atmospheric density. So does ambient air temperature and barometric pressure and things like that, altitude. We're going to discuss those all here very shortly. So real quick here, let's look at this basic illustration of a trajectory curve one more time and identify some of the different components of it, okay? The part where your bullet exits the muzzle, we're going to call that the origin. As the bullet is traveling up, because it begins to drop in respect to the line of departure, but it's still moving upwards physically. That's the ascending branch. That whole portion, anytime your bullet is getting farther away from the earth, that's the ascending branch. When it reaches the summit or the top of that, that's what we're going to refer to as the maximum ordinate, or the max ordinate. That's the highest point in your trajectory. And in a perfect frictionless environment, like if you're shooting on Mars, or not Mars, but on the moon, where you have no atmosphere, you're going to have a trajectory curve that's basically even, like we showed you before. But being that we do have an atmosphere, it's going to be skewed to the left. So the max ordinate's usually going to be 65 to 60% of the way to the target. So it's going to be skewed just a little ways past dead center, usually. The descending branch is after the summit, or the maximum ordinate. After the high point, your bullet begins to descend on its way down towards its final approach to the target. That's called the descending branch. And then the whole base of the trajectory is just called the base of the trajectory. And then when it reaches the terminus, that's when it hits the target. So there's different aspects of projectile flight that we're going to discuss, and they're going to vary depending on what point in this trajectory curve they're at. And so I just thought I'd share those definitions with you early. We will review that again, as we go on. But I just thought I'd get that these terms straightened out first. So just one final review here, one more time, before we actually start to look at some ballistic tables and how they're applied to do firing solutions. We want to just talk about the primary effects on projectile trajectory one more time. So you have two main things that affect a projectile's trajectory. The first one, as we said, was gravity, and that is constant. That's going to be the simple part of the math. The extremely complex part of the math that everyone argues about, that gives you all the different possible functions, is your drag characteristics. They hinge not only on the bullet's ballistic coefficient or its efficiency. We discussed that in projectile dynamics. The better ballistic coefficient is going to deal with these things better. It's going to cut through atmosphere better. So atmosphere and atmospheric density are going to have less effect on a bullet with a higher ballistic coefficient. So basically, the sum total of all the stuff affecting the drag on the bullet is going to affect the horizontal part of the trajectory, the horizontal part of the velocity, and the gravity is going to be a constant, which is that's the part determining your vertical portion of your velocity, and that's why you have that velocity or that trajectory curve shaped the way it is. It actually does get a lot more complex than this. We'll discuss this in a lot more detail. We're going to talk about Coriolis and spin drift and a lot of other things that happen in trajectory in our advanced ballistics. But for now, let's move on to the next portion of this video. And most of you are probably aware of this, but there's quite a few that are brand new to long-range shooting, and they might not have any idea how this even gets tackled.